A plain length of copper wire dangling from a wooden pole can harvest real electrical energy straight out of the sky. No solar panel, no battery, no moving parts, and zero grid connection. Just $12 of hardware store metal, a ground rod, and the atmosphere above your head. If you paid a massive electricity bill last month, you already paid for a deep cultural confusion, because nobody tells you the difference between voltage and power, and that difference is everything. The device is real. The physics is real. But the honest story of what it can actually do has been buried under a century of mythology that was always more profitable than the truth. The atmosphere carries a natural voltage gradient of around 100 to 200 volts for every single meter of altitude. A wire rising 10 meters into the air is sitting inside a genuine 1,000-volt electrical field, but potential without flow is just water pressure in a sealed pipe. At ground level, the actual current density is a microscopic 3/trillionths of an ampere per square centimeter. To collect just one single watt of continuous power, you would need an antenna array the size of a football field. It is a physics boundary, not a product limitation. The atmospheric field is too diffuse for bulk power. It will not run your air conditioner, it will not spin a compressor, and it will not erase your household utility bills. This technology is incredibly beautiful for low power sensor networks, but as a primary energy source for a modern home, it hits a wall. But if that principle surprises you, the idea that a massive physical field we walk through every day contains real energy in quantities too small to sell, but too useful to ignore, then we need to look at where the physics actually works at a domestic scale. Because the exact same pattern of ignoring simple, ambient fields has locked us into a brutal cycle of paying utility companies to solve problems that basic thermodynamics can handle for free. Right now, millions of people are running 3,500-watt compressors to fight the summer heat, completely unaware that an elegant, zero-electricity solution is staring them in the face. What if I told you that you could achieve a sustained 68 Fahrenheit inside your home when it is a blistering 102 Fahrenheit outside? What if you could drop local temperatures by 35 Fahrenheit in the middle of a bone-dry desert using a passive system that costs less than $40 to build? This is not a thermodynamic miracle, and it is not a scam. It is the physics of phase change, salt crystallization, and adiabatic cooling. Heat is not a permanent state. It is a fluid enemy that can be directed, trapped, and forced to work against itself. Just like the copper wire taps into the atmospheric voltage field, simple DIY setups can tap into local humidity gradients and thermal mass to drop temperatures completely off the grid. You do not need a multi-thousand-dollar HVAC split system to survive the summer. You do not need to be dependent on a fragile electrical grid that charges you premium rates when the sun is at its hottest. By understanding how water molecules absorb latent heat when they transition from liquid to gas, and how specific salt solutions act as a thermal cold battery, you can build infrastructure that cools your living space silently, reliably, and automatically. In this series, we are going to strip away the marketing fluff and the corporate suppression myths. We are going to look at the hard numbers, the exact flow rates, the science of convection towers, and the precise mechanical layouts of passive systems that require zero electricity to operate. I am going to show you the step-by-step logic of how to build these systems using basic materials from the local hardware store, the critical engineering mistakes that cause most DIY builds to fail, and how historical civilizations successfully cooled massive mud brick cities in the hottest climates on Earth without a single watt of power. The grid wants you to believe that comfort requires a subscription. The physics proves otherwise. Let's find out how it works. To defeat the heat without a power grid, you must first stop treating cooling as something you manufacture. Air conditioning has conditioned us to think that cold is a substance you pump into a room, like water into a bucket. It is not. Cold does not exist. There is only heat, which is kinetic energy at the molecular level, and the absence of heat. When you run a compressor, you are using brute mechanical force to compress a refrigerant gas, forcing it to drop its heat outside, and then allowing it to expand inside to absorb energy from your air. It is incredibly energy intensive because you are fighting the natural gradient of the universe. Passive cooling is the art of creating an open thermodynamic pathway that coaxes heat to leave your living space on its own accord, to make a $40 system drop an interior space to 68 Fahrenheit when it is 102 Fahrenheit outside. We rely on three foundational pillars of physics: sensible heat versus latent heat, vapor pressure differentials, and thermal mass battery storage. Let's look at the first mechanism, adiabatic evaporation. This is the core engine of non-compressor cooling. When water changes state from a liquid to a gas, it requires a massive injection of energy to break the hydrogen bonds holding the molecules together. This energy is called the latent heat of vaporization. For water, this value is exceptionally high, approximately 2,260 kilojoules of energy per single kilogram of water evaporated. The crucial engineering distinction here is that this energy is not pulled from an electrical outlet. It is pulled directly from the surrounding air as thermal energy. When a stream of hot, dry air passes over a wet surface, the liquid water absorbs the sensible heat. The heat you can actually feel with a thermometer and converts it into latent heat within the water vapor. Because that thermal energy is now locked up in the molecular bonds of the vapor, the temperature of the air stream plummets. This is a strict adiabatic process, meaning no net energy is added or removed from the system. The energy simply changes form from high-temperature sensible heat to low-temperature latent heat. The mathematical limit of this cooling potential is defined by the wet bulb temperature. If you wrap a thermometer bulb in a wet cloth and swing it through the air, the lowest temperature it can possibly read, due to pure evaporation, is the wet bulb temperature. The drier the air, the greater the gap between the actual air temperature, the dry bulb temperature, and the wet bulb temperature. In a desert environment at 102 Fahrenheit with a relative humidity of 10%, the wet bulb temperature sits at roughly 63 Fahrenheit. That means pure, unassisted water evaporation has the theoretical potential to drop the airstream by nearly 40 Fahrenheit. But standard evaporative cooling carries a massive engineering drawback: humidity. As the water evaporates into the airstream, the relative humidity spikes toward 100%. If you blow this air directly into a house, it quickly becomes an unlivable, sticky swamp where human sweat can no longer evaporate, neutralizing your body's internal cooling mechanism. To break through this limitation without spending thousands of dollars, we employ indirect evaporative cooling. This requires a multi-channel heat exchanger. We split our airflow into two distinct pathways, the primary airstream and the secondary airstream. The secondary airstream passes through a series of channels lined with a constantly wetted capillary material. As this secondary air passes through, water evaporates into it, dropping its temperature down toward the wet bulb limit of 63 Fahrenheit. This cold, hyperhumid secondary air passes along the opposite side of a highly conductive material, like thin aluminum sheeting or specialized waterproofed plastics, flanking the dry primary airstream. Because the aluminum plate is cold, heat transfers out of the dry primary air and into the wet secondary airstream. The primary air never touches the liquid water. It never absorbs water vapor. The sensible heat is drained out of it through the conductive wall. The result is an output stream of fresh, dry air dropped down to 68 Fahrenheit, with its original comfortable humidity level intact. A hot, wet secondary air is exhausted entirely outside the building, carrying the home's interior heat away with it. Now, what happens if you live in an environment where the ambient relative humidity is already high, say 60% or 70%? In these conditions, the air is already saturated with water vapor, meaning the vapor pressure differential between the liquid surface and the atmosphere is minimal. Evaporation slows down or stops entirely. The wet bulb temperature sits too close to the dry bulb temperature to provide significant cooling. This is where salt chemistry comes into play, acting as a chemical compressor. Certain salts are highly hygroscopic, meaning they have a powerful natural affinity for water molecules. When these salts dissolve in water, they form a brine solution with an incredibly low vapor pressure. If you expose humid air to a concentrated solution of calcium chloride or lithium chloride, the water vapor in the air is forcibly pulled out of the gas phase and absorbed into the liquid brine. This process is called liquid desiccant dehumidification. By running humid ambient air through a basic, low-cost packed column or a series of saturated matrix filters soaked in a concentrated calcium chloride brine, you strip the moisture out of the airstream without using a single mechanical cooling part. The air leaves the desiccant chamber bone dry. Once the air is dry, its wet bulb temperature drops precipitously. You can then route this newly dried air directly into your indirect evaporative cooling stage. The salt matrix essentially resets the environmental clock, turning sticky coastal air into dry desert air, which can then be deeply cooled via pure evaporation. The engineering challenge with desiccants is that as they absorb water, they become diluted and lose their effectiveness. They need to be regenerated. In a high-tech industrial setup, this is done with electric heaters. In a practical off-grid setup, we use a passive solar regenerator. The diluted brine is trickled down a black, sloped solar collector plate exposed to the sun. The solar thermal energy heats the brine, raising its vapor pressure and driving the captured water back out into the ambient atmosphere as steam, reconcentrating the salt solution so it can be looped back into the house at night. The final piece of the passive architecture is managing the velocity and storage of this thermal energy, which brings us to the physics of thermal mass and diurnal temperature swings. Air has a very low volumetric heat capacity, roughly 0.0012 joules per cubic centimeter per degree Celsius. Water is roughly 3,500 times denser in terms of heat storage capacity. Solid materials like adobe, stone, and high-density mud brick sit squarely in the middle, capable of storing immense quantities of thermal energy per unit volume. Think of high-density material as a thermal sponge or a cold battery. In regions with a high diurnal temperature variation, where the daytime temperature hits 102 Fahrenheit but drops to 60 Fahrenheit at night, the building envelope itself can be engineered to flatten the temperature curve. A wall built with the correct thickness of stone or adobe creates a thermal lag. Heat does not move instantly through solid matter. It migrates as a wave via conduction. By calibrating a wall to have a 12-hour thermal lag, the intense thermal energy striking the outside of the building at noon does not reach the interior surface until midnight, when the outside air is cold and the heat is actually welcome. Conversely, the cold of the desert night is stored deep within the core of the masonry. During the blistering heat of the following afternoon, the interior walls remain physically cold to the touch, acting as a massive radiant heat sink that absorbs the radiant energy emitted by human bodies and ambient air. To supercharge this effect without electricity, we introduce natural convection currents via a solar chimney. A solar chimney is a vertical shaft painted deep matte black with a glazed glass face oriented toward the sun. The air inside the top of the chimney absorbs solar radiation, heats up rapidly, expands, and becomes less dense. Because hot air naturally rises, it surges out of the top of the chimney at high velocity. This creates a powerful, continuous, low-pressure zone at the base of the chimney inside the house. To equalize this pressure drop, air is forcibly sucked into the home from the opposite side of the structure. If you position your air intake through an underground earth-to-air heat exchanger, a series of smooth pipes buried 2 meters deep where the soil temperature remains at a constant, stable 55 Fahrenheit year-round. The incoming air is pre-cooled by the earth before it even hits your living space. This is a complete self-regulating fluid dynamics loop. The hotter the sun shines, the faster the solar chimney evacuates air, and the faster cool subterranean air is drawn into the house. No fans, no wires, no moving parts. Just pure pressure differentials driven by density variations in the fluid medium of air. By combining the latent heat transfer of indirect evaporation, the chemical drying power of salt brines, and the raw kinetic storage of thermal mass, you create a home that functions as a self-cooling organism. In the next part, we will look at how to construct a functional version of this system using off-the-shelf components from a standard hardware store. To build a functional zero AC passive cooling matrix for under $50, you must think like a fluid dynamics engineer rather than a consumer assembling a retail kit. The goal is to construct a modular, non-electric, two-stage indirect evaporative cooler integrated with a liquid desiccant module using off-the-shelf industrial components. This setup will mechanically separate the wet exhaust air from the dry intake air while allowing full thermal exchange. The core bill of materials requires exactly 5 items easily sourced from a local hardware store or agricultural supplier. 2 heavy-duty 5-gallon food-grade plastic buckets 8, a 25-foot roll of 4-inch diameter flexible aluminum foil ducting 12, a 50-pound bag of industrial-grade pelletized calcium chloride 18, a highly porous, non-rotting capillary medium such as cocoa coir liner or fibrous cellulose cooling pads 7, and a 10-foot length of 1 2-inch PVC Schedule 40 pipe with a manual ball valve 5. First, let us construct the heart of the machine, the dual-chamber indirect heat exchanger. Take your 25-foot roll of flexible aluminum ducting. Aluminum has an exceptionally high thermal conductivity rate, roughly 205 watts per meter Kelvin, making it the ideal material to allow heat to pass through while acting as a total physical barrier to water vapor. Compress the flexible aluminum ducting slightly so that it forms a tight, continuous vertical helix or coil that fits snugly inside the first 5-gallon bucket. This aluminum coil will carry your primary airstream, the fresh, dry intake air meant for your living space. The space inside the bucket surrounding the outs of this aluminum coil is your secondary chamber. Line the outer surface of the aluminum coil completely with your capillary medium. Wrap the fibrous cellulose or cocoa coir tightly around the aluminum ridges, securing it with zip ties. This ensures that the wet cooling pad is in direct, physical contact with the highly conductive aluminum walls. Next, drill a 4-inch entry hole through the lower side wall of the bucket, right above the base, and a 4-inch exit hole through the opposite upper rim of the bucket. Route the lower end of your aluminum coil out through the bottom hole, and seal the gap completely with waterproof marine-grade silicone adhesive. Route the upper end of the coil through the top hole and seal it identically. The interior of the aluminum tube is now a sealed, isolated pneumatic pathway. Air passing through it will dump its heat into the bucket, but can never pick up a single drop of moisture. To automate the wetting of the capillary medium without an electric water pump, we construct a gravity-fed drip manifold. Drill a series of 1/16-inch holes spaced exactly 1 inch apart along a ring of 1 2-inch PVC pipe, calibrated to sit perfectly flat on top of the coiled capillary medium inside the bucket. Connect this ring to your second 5-gallon bucket, which is mounted on a shelf or platform at least 3 feet above the main cooling unit to act as a gravity-fed header tank. Install the manual PVC ball valve on the downspout line. When you crack the valve open slightly, water flows down via hydrostatic pressure, fills the distribution ring, and trickles evenly onto the top of the capillary medium, saturating the entire length of the vertical column via gravity and capillary action. Any excess, unevaporated water collects at the bottom of the main bucket, where a 1/2-inch bulkhead drain fitting routes it out to a collection pan or a garden bed. Now we introduce the fluid propulsion mechanism. Because we are avoiding electrical fans, this system must be physically coupled to a solar chimney or a dedicated convective thermal flue, the exit port of the wet secondary chamber. The open space inside the bucket surrounding the coil must be piped directly into the base of your solar chimney. As the sun beats down on the black chimney face outside your home, the air inside it expands and rushes skyward, pulling a powerful vacuum on the secondary chamber of the bucket. This vacuum forcibly sucks hot, dry outdoor air down through the top of the bucket, pulling it straight through the wet capillary matrix. As this airstream passes through the wet matrix, water rapidly evaporates into it, dropping the temperature of that secondary air down toward the wet bulb limit. This hypercooled air chills the thin aluminum walls of the internal coil. Simultaneously, the main intake line of the aluminum coil is routed to an open window or an earth tube. The suction from the sluice forces fresh, clean outdoor air through the inside of the chilled aluminum helix. The heat from this intake air instantly flashes through the aluminum wall into the cold, wet exhaust stream. You are left with a continuous blast of fresh, dry air entering your room through the center of the coil, dropped by up to 35 Fahrenheit, depending on your starting ambient humidity. If you are operating this system in a high-humidity coastal region, you must install the liquid desiccant dehumidification module directly upstream of the cooling bucket. Take a 4-inch PVC pipe joiner coupler and pack the interior tightly with the pelletized calcium chloride. As the humid ambient air stream is drawn through this packed chemical bed before entering the cooling module, the calcium chloride pellets greedily absorb the water vapor from the air via chemical deliquescence. The air exiting the chemical bed is now completely dried, dropping its wet bulb temperature and allowing the subsequent evaporative stage to function at peak thermodynamic efficiency. The 3 most critical engineering mistakes made by beginners during this build involve grounding, vapor sealing, and fluid balancing. First, if your gravity-fed drip manifold delivers water too fast, it will flood the secondary chamber, drowning the airflow and stopping evaporation entirely. The ball valve must be dialed in to deliver a precise microdrip that matches the local evaporation rate exactly, typically between 0.5 to 1.5 liters of water per hour of operation. Second, any failure in your silicone seals around the aluminum duct ports will cause catastrophic vapor cross-contamination. If wet, humid air from the secondary chamber leaks into the primary intake line, your room will instantly transform into an unlivable, humid greenhouse. Test your seals by capping one end of the aluminum tube and blowing smoke or pressurized air through it to look for micro fissures before final installation. Third, system placement is everything. The main cooling bucket must be kept entirely in the shade, ideally semi-buried in the ground on the cool north-facing side of the structure or inside a dedicated cellar space. If the outer plastic shell of the bucket is exposed to direct solar radiation, the ambient heat load will overwhelm the conductive capacity of the internal aluminum coil, neutralizing your cooling differential. The solar chimney, conversely, must be placed on the south-facing wall or roof with zero obstruction from trees. Maximize its thermal gain to ensure continuous, unpowered airflow to precisely test and calibrate your system. You cannot rely on cheap household thermometers. You need two digital dual-probe psychrometers placed at the primary intake and the final output vents. Measures both the dry bulb temperature and the relative humidity simultaneously. If your system is balanced correctly, you will observe a massive drop in dry bulb temperature across the primary line while the relative humidity remains completely stable or drops slightly, confirming successful indirect thermal transfer without vapor migration. In the next part, we will examine how these exact geometric formulas have been successfully deployed at a macro scale in some of the most unforgiving, hot off-grid environments on the planet. To prove that these systems work at scale, we have to look past modern industrial architecture and examine the field data from the most hostile thermal environments on the planet. For thousands of years, civilizations in the Persian desert, the Indus Valley, and the high arid plateaus of North Africa built massive, multi-story urban centers where interior temperatures remained at a stable 70 Fahrenheit while the outside air was hot enough to melt asphalt. They did not have access to electricity, copper wiring, or mechanical compressors. They solved the thermodynamic equation using raw geometry, local geology, and microclimatic pressure management. The most sophisticated historical manifestation of this is the traditional Persian badger, or wind tower. These are tall, vertical masonry structures protruding from the roofs of desert buildings, engineered to exploit two distinct microclimatic forces: pressure differentials caused by regional winds and the chimney effect driven by temperature variations. The tower is internally segmented into vertical shafts using structural brick baffles. When a desert wind hits the top of the tower, it hits a high-pressure zone on the windward side. This forces the hot, moving air down into the windward shaft. As this hot air travels downward, it passes over thick, heavy clay or stone walls that have been cooled by the radiation of energy into the clear desert night sky. The wall acts as a giant sensible heat sink, draining energy out of the descending airstream before it ever enters the living space. Simultaneously, the leeward side of the tower experiences a low-pressure zone due to aerodynamic lift over the structure. This low pressure sucks the hot, stale interior air up out of the building and exhausts it back into the atmosphere. The entire house becomes a continuous, self-powering respiratory system, but the ancient engineers did not stop at pure convection. To supercharge the system, they coupled the wind towers with a qanat, a vast network of subterranean aqueducts that transported water from distant mountain aquifers beneath the desert floors. The deep vertical shafts of the wind towers were dug down until they intersected directly with the flowing water of the qanat. When the hot, dry desert air was forced down the wind tower shaft and pushed across the surface of the underground water, it underwent immediate, massive adiabatic evaporation. The water absorbed the sensible heat from the air, dropping the air temperature down to the local wet bulb limit of roughly 60 Fahrenheit. Because this hypercooled air was incredibly dense and heavy, it naturally flowed downward into the lower living quarters and underground earthen cellars, known as shawadans, displacing the lighter, warmer air and creating a localized thermal oasis without a single mechanical moving part. In modern off-grid engineering, we translate these exact geometric principles using high-performance, low-cost materials. Look at the earthship architecture pioneered in the high deserts of New Mexico, where ambient temperatures fluctuate from sub-zero winters to blistering 100 Fahrenheit summers. These structures are built with rammed earth tires, massively dense thermal batteries that form the north, east, and west walls of the building, coupled with a highly glazed southern facade. Instead of an ancient qanat, modern passive houses use earth tubes, also known as earth-to-air heat exchangers. A series of smooth-walled, high-density polyethylene or PVC pipes, roughly 6 to 8 inches in diameter, are buried at a depth of 2 to 3 meters below the surface. extending horizontally for 100 to 150 feet before entering the home's lowest floor level. At that depth, the thermal mass of the earth completely dampens the seasonal temperature fluctuations of the surface. The soil temperature remains at a constant, unyielding baseline year-round, typically between 50 Fahrenheit and 55 Fahrenheit across most temperate and arid zones, when hot outdoor air is drawn through these underground lines. Heat continuously migrates out of the airstream and into the surrounding soil via pure conduction. The air enters the home pre-cooled to a refreshing 58 Fahrenheit, entirely bypassing the need for an evaporative stage if the local humidity is already low, to drive this airflow without a utility connection. Modern off-grid builders install a high-efficiency solar chimney on the highest point of the roof, facing true south. The chimney is constructed using a simple wooden frame lined with matte black painted sheet metal and fronted with a layer of tempered solar glass. The air inside the glass chamber easily hits 150 Fahrenheit under direct sunlight. This extreme temperature differential causes the air to expand violently and rush upwards out of the top exhaust vents. The vacuum pressure created at the base of this chimney inside this house is so immense that it continuously draws air through the subterranean earth tubes at a velocity of several meters per second. The hotter the sun beats down on the roof, the faster the solar chimney evacuates air, and the more cold, earth-cooled air is sucked into the living space. This is the ultimate rejection of the modern HVAC paradigm. A standard air conditioning system works harder and draws more grid power as the outside temperature rises, placing maximum financial and mechanical stress on the homeowner precisely when the system is most vulnerable to failure. A solar chimney earth tube matrix does the exact opposite. It scales its cooling output linearly with the intensity of the sun. It uses the environment's own extreme energy to fuel the mechanism that defeats it. When you study these case studies, from the 1,000-year-old clay towers of Yaz to the modern earth-insulated homesteads of the American Southwest, the lesson is uniform. The difference between comfort and misery off the grid is not a question of financial budget or high-tech equipment. It is a question of matching your building's geometry to the thermodynamic realities of your specific topography. In the final part of this series, we will break down the precise economics of this approach, look at the scaling limitations you must account for, and calculate exactly how much money you are leaving on the table by staying tethered to the traditional electrical grid. To fully understand the leverage of passive infrastructure, we have to look at the cold, unyielding reality of utility economics. The modern energy grid is a highly centralized system optimized to sell you a recurring commodity, the kilowatt hour. When you turn on a standard 3,500-watt central air conditioning unit, it consumes roughly 3.5 kilowatt hours of electrical energy for every single hour it runs. If you operate that system for 12 hours a day, over a 30-day billing cycle in a hot climate, you are consuming roughly 1,260 kilowatt hours of electricity purely for thermal management. At an average utility rate of $0.06 per kilowatt hour, that single appliance costs you over $200 a month. In extreme zones like California, Texas, or parts of Europe where peak pricing can easily soar past $0.35 per kilowatt hour, your monthly summer cooling bill can devastate a household budget. Now, consider the life cycle cost of that mechanical infrastructure. A high-efficiency heat pump or split AC unit costs between $4,000 and $10,000 to purchase and install. It relies on complex electronic control boards, high-pressure scroll compressors, and chemical refrigerants that degrade over time. The system carries an average operational lifespan of just 10 to 15 years before mechanical fatigue, or a microscopic refrigerant leak renders it useless, forcing another massive capital expenditure. Contrast this directly with our $40 passive indirect evaporative matrix coupled with a solar chimney. The capital cost is a microscopic fraction of a commercial unit. Because the fluid propulsion is driven by density variations in solar heated air, the operational utility cost is precisely $0. There is no electrical bill because there is no electrical draw. Over a 10-year horizon, assuming a conservative average cooling bill of $150 per month for only 4 months of the year, a standard mechanical AC system will drain at least $6,000 in raw electricity from your bank account, plus an additional $2,000 to $3,000 in maintenance, fan replacements, and eventual system depreciation. The passive system, built from inert polymers, local soil, and hardware store metal, completely reclaims that $9,000 leakage. It acts as a permanent structural investment that pays a tax-free dividend every time the sun shines. However, as engineering educators, we must completely reject the unscientific, utopian claims found on the fringe internet. Passive cooling is not a magic wand that works instantly everywhere. It is bound by strict geographic, thermodynamic, and volumetric scaling limits that you must accurately calculate before committing to a build. The first major limitation is the climate boundary. Pure evaporative and indirect evaporative cooling systems require a significant wet bulb depression to function. If you live in a deep, humid subtropical climate, such as America's Gulf Coast, Southeast Asia, or coastal Brazil, where the ambient summertime relative humidity routinely sits at 85% or 90%, the wet bulb temperature is practically identical to the dry bulb temperature. In those specific conditions, an unassisted evaporative cooler cannot drop the air temperature by more than a couple of degrees. While our liquid desiccant module using calcium chloride brine can bridge this gap by mechanically absorbing air moisture, it scales up in complexity. You must build a massive dedicated solar regeneration array outside to constantly evaporate the captured water out of the brine, turning the system into a continuous chemical management project. The second major limitation is volumetric flow rate and cooling density. A mechanical air conditioner uses a high-power motorized fan to forcibly push thousands of cubic feet of air per minute through tight, compact ductwork. Passive systems, relying on the gentle thermal buoyancy of a solar chimney, generate significantly lower static pressure. To move the same volume of air, your pathways must be physically massive. You cannot run an earth tube through a restrictive 2-inch pipe. You need a smooth, wide 6-inch or 8-inch smooth-walled conduit to minimize fluid friction against the pipe walls. Your building layout must be designed from the ground up to allow unrestricted, laminar airflow from the cool intake side to the hot exhaust stack. Scaling a passive house up means scaling the architectural footprint, not just dropping in a bigger box. No. If you try to cool a poorly insulated, thin-walled modern stick frame trailer using a tiny 5-gallon bucket cooler, the local solar heat gain through the uninsulated roof will wildly outpace the system's latent heat absorption rate. The house behaves like a leaky bucket. You are pouring cold air into a sieve. To make passive cooling work at a large scale, the home must be heavily insulated, tightly sealed against uncontrolled drafts, and paired with significant interior thermal mass to store the nighttime cold. But if you are willing to work within these real boundaries, if you accept that engineering is about optimizing trade-offs rather than chasing miracles, the rewards are profound. A world of small, decentralized structures that graze on ambient environmental fields is not a primitive step backward. It is the ultimate evolution of independent infrastructure. You do not need to wait for a centralized grid to become cleaner, cheaper, or more reliable. You do not need to remain a passive consumer trapped in a cycle of escalating monthly subscription costs just to keep your living space safe and livable. By mastering the simple physics of pressure differentials, phase changes, and thermal lag, you can claim absolute sovereignty over your immediate environment. You can build a home that breathes, cools, and regulates itself silently and automatically, using the very heat of the sun to fuel its own defense. If this engineering journey has changed the way you look at the physical fields and thermal gradients built into the world around you, make sure to hit that subscribe button, turn on notifications, and drop your build measurements in the comments below. In our next series, we are going to dive deep into the science of thermoelectric materials and the Seebeck effect, exploring how a simple temperature delta can create an eternal solid-state electrical current. The physics is ready. The tools are in your hands. Stop paying for the confusion, start building within the real numbers, and I will see you in the next video.